And welcome to problem number 9 on the 1.5 topic questions. You've read the problem, hopefully the picture matches. Now, I know that I drew it this way because I couldn't help but recall that the gravity on the moon is less than the gravity on Earth. So if I launch something horizontally, and notice my notation, the initial speed was v, all horizontal. I'm going to help myself see that by saying that v is actually vx naught, horizontal. There's no velocity in the y direction. If the downward acceleration is less on the moon, then it should take more time for this thing to hit the ground. So it should go farther since they're both going at the same velocity. So that's why I drew it this way. But I could be wrong. I mean, if this wasn't the moon or I didn't know what the velocity, the accelerations were, I might draw a picture like this, but I would have to remember that I don't know how these relate. Okay? But since it's the moon, I'm going to use this picture. I'm not going to use the fact that I know GM is smaller than GE to arrive at the answer. So we're just going to go all math model. We're really trying to find this ratio in terms of GE and GM. What do both projectiles have in common, the Earth and the Moon projectiles? They both fall from the same height. Horizontal velocity only, that means Vy naught 0. Ding, ding, ding. 0, 0, 0. I'm not interested in time at all, so this doesn't really float up as like, well, yeah, I'm not sure. I'm right away thinking about this just because there's no time involved. I just have a distance that I need to fall. So if they both fall a distance h, my delta y is the same between the two, and I've just got I've got an acceleration, right? So this is either GE or GM. This is 0, but actually I'm not sure this last equation is going to help because they could hit at different velocities, right? They fall through h, but they have different g's. So they might land at their vertical velocity might be different. They both have 0 initial velocity, so that makes this equation a little simpler, okay? And they have the same horizontal velocity, so there's a time element here as well. So I'm going to write this one out because I've got x's, and then we'll take a look at this 0 either, well, maybe one of these. Okay, so let's see what happens. Okay, so I'm just going to start with, let's start with the Earth. I'm going to write an expression for, because since I want that, right, so I'm going to say the travel time of the Earth is equal to v, because vx naught is v. That's just v times time of travel on the Earth. The time of xm is equal to v times the time of travel on the moon. So if I just take a ratio of these two right away, just because I want to start thinking in terms of that, I get VTE over VTM, which is just the ratio of time on Earth to time to moon. The V's cancel. How long is it in the air on Earth? Well, I know that my initial velocity is 0, so I can do this. H is basically what? It's, if I say y naught is 0, well, let's go this way. Right? If I fall from 0 to a y, oh wait, if I'm going to use minus gt, what's the system? I've got to be up being vertical. So really it's this. My initial velocity is 0. My final velocity is y. Okay, my h is actually my delta y, so it's y minus y naught. Okay, so let's see what happens. If I'm going to keep this so that I don't have to change my equations. Up is positive. I'm going to fall. So if I fall, let's try, I really don't want to deal with any final y velocities, so let me just try this one. And why is that? Because I don't know what that is. Let's see, do I know what this is? Yes. Well, that's basically h, right? If this is 0, this is h. Do I know what this is? Yeah, it's 0. Okay, so on the Earth side, let's go, I'll just write out my general equation. Okay, on the Earth side, I have h is equal to 0, because if this is 0, then my final y coordinate is h, plus my initial y velocity, that's 0, minus 1/2 g e t e squared. On the moon side, I fall through the same height. Everything else is 0 as well, right? 0 plus 0. This is going to be minus 1/2 g m t m squared. Now, since I'm falling, I should pause for a sec. If I'm falling, my initial is 0, and my final position is 0. So I should have done this. I should have gone final position is 0 since I'm falling. And my initial position, if up is positive, that's h. So this should be 0, that should be h. And now, if I rearrange this, I get minus h is equal to minus 1/2 gte squared. Minus h is equal to minus 1/2 gtm squared. The nice thing is the negatives cancel. So I can get an expression for te squared. Te squared, if you do the math, I'll skip all the tiny algebra. You're expected to have mastered that. That's going to be what? 2h over g. Oh, ge. Te squared is 2h over g. And likewise, tm squared is just going to be 2h over, gm there, gm. Home free? Almost? Because I've got te over tm. I've got te and tm there. So if I take the square root, if you really want to see that, then I've got te is just going to be the square root of all this. Or another way you can do it is it's to square these ratios. And tm is just going to be the square root of all this. So xe over xm is equal to te, which is the square root of 2h over ge, all over the square root of 2h over gm. What's that equal to? That's equal to the square root. This is on the bottom, so it flips up, right? So I take the reciprocal, it's based, and the two h's cancel. You could do the math, dot, 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 gm over ge. So the answer should be A. And that is problem number 9.